Really want to thank the folks from IceCube for inviting Wednesday night at the lab to be part of this splendid occasion to mark the 10th anniversary of first light at the IceCube Observatory at the South Pole. When I first came to Madison in 1991, one of my colleagues was writing a newsletter out of the Biotech Center, and he knew about Amanda. And I just thought it was a song. And he was talking about these things that you might be able to detect or not detect in ice in the South Pole. It was one of the most astonishing scenarios I'd ever heard. So it's been an amazing 30 years to see how the folks at this table and their colleagues, not only here at UW-Madison, but at places all over the country and all over the world, are figuring out how to design, build, stick in the ice, and get to work this most remarkable, largest observatory on the planet. Well, I don't know if it's the most remarkable. I bet there are other observatories that would argue with that, but it is the biggest. Is that
True.
okay? We're gonna go with the biggest.
Definitely the strangest.
Thank you.
We can have a vote.
So I'm just going to introduce the three folks that are here real briefly. Professor Lulu, my left, your right, and they're Dr. John Kelley and Professor Francis Halzen. I don't know who's going to go first.
I'm going first.
Thank you very much. Again, it's a great pleasure to have you here. Professor Halzen gave a very early talk in the series. We've been doing this series since February 22nd of 2006. And I think you were here in 2006 when we were still next door in the conference room. I really appreciate the support that you and many of the IceCube folks have given to Wednesday night at the lab over the years. Would you please join me in welcoming the three of our presenters to Wednesday night at the lab.
Thank you so much. We're delighted to be here at this special Wednesday night at the lab presentation to talk to you both in person, which is amazing. I haven't done this for so long, and to our remote participants about the IceCubeNeutrino Observatory. And yeah, we were debating if is it the biggest, is it the, but I think it's definitely one of the strangest observatories out there. And as University of Wisconsin is the hub for operations of this detector, in particular the Wisconsin IceCube Particle Astrophysics Center, although it's really a worldwide collaboration and worldwide effort. So three of us are going to talk to you this evening. I'm going to kind of give some background, some history, but also talk about why would we want to build a neutrino detector in the first place and how did we do it? And then Professor Halzen will talk about what we have learned, the science that we've been able to do in the first 10 years of IceCube operations. And then Professor Wu will tell us about what is next for IceCube and neutrino astrophysics in general. So to give some motivation to this concept, I want to turn to, let's say, traditional astronomy, astronomy with visible light. And this is a beautiful image from the Hubble Space Telescope of a star that exploded in 1054. This is a supernova, and this you can see this greenish image of these fragments of the star after it exploded. And as amazing as this image is, if we actually look at this in X-rays, instead of in visible light, and this is a sequence of images from the Chandra X-ray Observatory, we can actually see into this nebula and see that at the core, there's this spinning neutron star left over from the death of the progenitor star. And we can see that you can see the shock waves plowing into the supernova remnant and these jets that are emitting from the spin axis of the pulsar. And so the point is here is that by looking at this object in another wavelength of light, we can see totally different things than just this optical image from Hubble. And so that kind of motivates us to, what if we could take this a step further? What if we could look at the universe not in just light or another wavelength of light, like X-rays, gamma rays, radio? What if we could look at the universe in neutrinos? And you may say, okay, that's fine, that's all good, but what is a neutrino anyway? So let's step back and think about the particle physics for a minute. We might not be as familiar with neutrinos because everything around us is typically made up of just protons and neutrons, which are up and down quarks, and electrons. But the electron actually has a neutrino counterpart, the electron neutrino. And the electron also has some heavier cousins, other particles that are like the electron, but heavier and they decay, like the muon and the tau. And each one of those also has a corresponding neutrino of the same type, or in particle physics, we call it flavor. So we've got the electron neutrino, the muon neutrino, and the tau neutrino. And these neutrinos, unlike the electrons and the muons and the taus, they don't have any electric charge. And they only feel the weak nuclear force, which means that they will just typically zip through normal matter. They will go all the way through a planet, all the way through a star without interacting or colliding with anything. Other things that we know about them, we know they have some mass, but it's so small we don't know what it is yet. We're still working on that. And Lou will also tell you how they can actually change from one flavor or type to the other. Now let's talk about some sources of neutrinos. Don't stop eating fruit, but your bananas actually have trace amounts of radioactive potassium-40 in them, which decay. And so your banana is producing neutrinos, but don't worry. Again, they just zip through your hand and zip through all the earth and go out the other side and go into outer space, so no worries. Actually, one of the most prolific sources of neutrinos is the sun. So the sun is this engine of nuclear fusion. And these nuclear reactions in the sun produce huge numbers of neutrinos. Supernova, we saw the Crab Nebula. That's one example of the supernova. One that happened most recently that was close by in the Large Magellanic Cloud is supernova 1987A. Those also produce huge numbers of neutrinos. But what if we think even bigger, even more extreme, more energetic objects in outer space? Like these supermassive black holes at the center of other galaxies. Some of these supermassive black holes have these superheated plasma disks around the black hole. And again, these energetic jets, which you can see in this multi-wavelength image coming out of the spin axis of the galaxy. What if we could look at those objects in neutrinos? So the next problem is, okay, how do we detect a neutrino? And the number one, let's say, thing that you need to detect a neutrino is really patience. Because we can't focus the neutrinos, we can't trap the neutrinos. We basically need a giant target for the neutrinos, and then we have to wait. And again, most of the neutrinos are just zipping right through that target medium. But occasionally, we'll get lucky and one will collide or interact with our target. And then when that happens, some of these other particles, like a muon or electrons or other particles, can be produced. And those we can actually see. And by see, I mean in invisible light. There's an effect when a charged particle is moving through a medium at faster than the speed of light in that medium. That charged particle will actually produce Cherenkov light. And it's called the Cherenkov effect, and you can actually see in photographs of nuclear reactors this sort of eerie bluish glow. That's Cherenkov light from these charged particles in the water surrounding this nuclear reactor. So we need patience. We need a big target of something that's transparent, and we need light detectors. Those are the three ingredients for our neutrino detector. So the transparent material, we're on Earth. There's a lot of water. It's free. I've put a few arrows here. Those are not accidental. The Mediterranean, Lake Baikal, neutrino detectors there. But what we're going to talk about, because we're talking about IceCube, is the Antarctic ice sheet. So ice also works as a great target for neutrinos. And as it turns out, the ice in Antarctica at the South Pole is exceptionally transparent. And so this is an embarrassingly short history, and really Francis should be telling you about this because this was his idea in this paper with John Learned back in 1998 to actually build a neutrino detector at the South Pole using the ice as the target. And so in the introduction, you heard about some of the early efforts in the early 90s. There were tests in Greenland and at the South Pole to test this concept of using a light detector to detect particles in the ice via their Cherenkov light. And the Amanda detector, which was built in the 90s and up to 2000 at the South Pole, worked great, and it detected neutrinos. However, these are neutrinos that were produced in the Earth's atmosphere, which are interesting in their own right. But ultimately, the Amanda detector was a bit too small to catch those rarer high energy particles from objects in outer space. And so in about the late 90s and starting construction in 2004, that's where the IceCube detector comes in. So this is a diagram of the IceCube detector, and it really is at the South Pole, just across the skiway where the planes land. You can it's hard to see in the slide, but there's a little blue dot at the top of the screen. That's the South Pole Station where everybody lives. And then the concept of the IceCube detector is to put about 5,000 very sensitive light detectors into the deep ice from about 1.5 to 2.5 kilometers deep under the South Pole. And there's an example here. So we brought one of the DOMs. This is called a digital optical module, or DOM. And this business here, it's in a glass pressure sphere. And this part down here is the light sensor. It's called a photomultiplier tube. And then there are some electronics here, which read out the signal. And then this cable here, the connector is cut off, but if it had one, it would plug into one of these big cables or strings, which go all the way up to the surface and then connect to computers in a building at the South Pole. And there are 86 of these cables or strings, and about 60 DOMs per string. And you can see here how the concept of how the detector works. So we have in the diagram a muon neutrino coming in. Again, most of them are just going to go through the detector, but occasionally one will collide with the ice. Here it's produced a muon, and then the muon is leaving this trail of Cherenkov light through the detector. And the way to look at these kind of diagrams or snapshots of these events is that each one of these dots is a DOM that is lit up, and we'll show you a few of these. And the color is the time. So red are the DOMs that saw light first, and greenish blue are the DOMs that saw light later. So by looking at the timing of when the DOM saw the light, we can actually tell what direction the neutrino came from. So I mentioned that IceCube construction started in 2004, and IceCube construction is really a drill project because we have to get these sensors down into the ice somehow. And the way that we did that was to drill holes with hot water. So each one of these strings, we had to drill a hole 2.5 kilometers deep. And this big camp is a bunch of hot water heaters and pumps, and it's connected to a very long hose up in the upper right. And then that's attached to a drill head, and that drill head just basically melts its way. I mean, it's spraying water and then recirculating water to melt a hole into the ice. And then before the water in the hole refreezes, the cable with the DOMs is lowered down into that hole. And I can show you a picture of that here. You can see this is a view on the left of one of the DOMs going down the hole. And then on the right, this is kind of what it looks like during string deployment. You can kind of see in the upper part of that photo, one of the DOMs attached to the cable, getting ready to be lowered down into the hole. And it took about 40 hours per hole to drill the hole, and then about 10 to 12 hours additionally after that to install each of the strings of modules. And so that took about 7 construction seasons. And you can see a bunch of happy faces here. This is a photo from 2010, and that's the last dom in the middle there. That's about getting ready to go down the hole, and everyone signed their names in Sharpie around the waistband here. And since then, so full detector operation with all 86 strings started in May of 2011. And the detector has really been running magnificently since then. This is a plot from basically 2011 until today of one of the trigger rates of the detector. One of my collaborators referred to this as the heartbeat of IceCube. And IceCube is seeing cosmic ray muons also at about 2,000 times a second. And you can see there's this annual heartbeat as the seasons go. But the point is that the detector has been running 99% of the time it's taking data or more. And the other good thing is because these are frozen into the ice, we can never service them. But fortunately, they rarely die. 98.5% of them are still taking data. The last 2 that died in December of 2018. And we do have problems. Things break in the computer lab at the surface. But fortunately, we have 2 people they're called our winter rovers that stay at the South Pole for a full year, even when it's too cold to fly planes in and out, so they're stuck there. And they can respond to any issues, get the detector running if it's not taking data. And then in the summer, which for South Pole is November to January, we're able to normally in non-COVID times send people down and do new calibrations, computer upgrades, swap out power supplies, which you can kind of see in some of these photos. But even after just a couple of months after starting full detector operations in 2011, we started seeing very interesting events. These are the first 2 extremely high energy neutrino events that we saw in August of 2011 and January of 2012. We nicknamed them Bert and Ernie. And again, you can kind of see a snapshot of the little movie here of what the detector saw. You can see the DOMs lighting up. It's just slowed down a lot. This event happens in a few millionths of a second. But this is only the beginning of the story. And to tell you more about the science, I'll turn it over to Francis.
Thank you, John. Okay, can you hear me? Okay, so I am going to talk about what we did with this detector in the last 10 years. And I'm going to introduce a neutrino and the apparatus in a slightly different way. Because after all, it's not just a detector that detects a particle called a neutrino, it's a telescope. And I'm going to try to get that concept across. Now, John talked about quarks, and I actually spent the first half of my career trying to prove that quarks existed, and they do. But in high school, this was what I learned. The world is made of protons, neutrons, and electrons. And protons and neutrons make nuclei, and then the electrons make atoms. And that's what we are and the world is. Well, there is a problem with that. Because some people noticed when you change a neutron into a neutron can decay into a proton and an electron. And they noticed when they saw this neutron decay that the proton and electron would go that way occasionally. And that violates all the laws of physics. There has to be something going that way to conserve energy, momentum. And Pauli said, there is a particle there. We cannot see it. He said, we will never see it. He unfortunately was wrong. And, but so that tells you what a neutrino does. The neutrino is kind of an agent that's present. Whenever neutrons change into protons and protons into neutrons, That's what we call nuclear physics. So the neutrino that one, is that it? Yeah. So remember that the atmosphere glows in neutrinos. Now I cannot move my slides anymore. Which one was it?
We click once
Hmm?
in the bottom left. There is an arrow in the bottom left.
You can do hide for you.
Ah,
Yeah, and try clicking once here. Click.
okay. All right, so the atmosphere makes neutrinos. This is a disaster, as you will see later. So now, instead of looking at a banana or at the sun, we are actually going to look at the universe. And this is a picture of the universe, as you would see it when you go out and look at the sky. However, this would not be the universe from Madison, because this is the galactic plane, which I don't think you can see from Madison because of light pollution. But I'm going to make the same point as John, but for the whole universe. So this is visible light. So now I'm first going to go in the direction of red light. So what happens when you make the light redder and redder? Well, eventually the universe, stuck again. The universe looks like this. This is much more dramatic than the pictures of the crab you saw before. That's not even a relation with what we saw before. This actually, the sky in microwave photons, there are 411 per cubic centimeter in the whole universe, including in this room. I can guarantee they're there. You don't see them, of course. So let's now move towards the other side of the spectrum, towards the red, very, very red. And the sky looks like this. The interesting thing is that this game of shifting from between blue and red light, it actually has an end. And it has an end around a wave, an energy of photons. By then, the light we call photons And when this energy becomes, or photons becomes 1,000 TeV, I will explain to you in a minute what that is, then suddenly this game doesn't work anymore. The universe turns black. And the only way to see that universe in very, very blue light is with neutrinos. People realized this in the 50s. Someone just had to build a telescope. That was the problem. Why is the universe turns black? Well, here is a particle of light, a light wave, and it's filled with this 411 per cubic centimeter photons, microwave photons. So to this photon that we're going to try to detect with our telescope, it's like it's moving through molasses. It never gets here. And it meets one of these microwave photons and then makes an electron and its antiparticle. Well, that's okay. Now we have an electron to look at, but that's the problem. Electron has an electric charge. And so the universe and our galaxy are filled with magnetic fields. So what happens is the same as that happened to this proton. It gets bent and the astronomy is lost. You know, the light beams don't come straight at us. We cannot make a picture of the sky anymore. They come from random directions. So only neutrinos avoid this problem. The only, I mean, here is the reason why to do neutrino astronomy. I don't need to do any propaganda here. The only problem with neutrinos is that they are difficult to detect. But here the summary of the slide, you know, from blue to red light, and then we eventually, you know, a quarter of the universe we have never seen. We actually know it exists because we see protons with those very tiny wavelengths, very high energies coming at us. So in this dark sky, there are huge cosmic accelerators that send these protons at us. In fact, we know how to build accelerators. I was going to tell you what 1 tera electron volt is, 1 TeV is. It's the energy of the accelerator at Fermilab before it was closed down, which is between here and Chicago. And now we have a better one in Geneva of 14 TeV. We see particles of 3 million TeV coming at us from the sky. I mean, how cannot you spend the rest of your life trying to find where they come from when you're a particle physicist? Forget those words. In fact, if I took the best magnets that exist today, I would have to go to Geneva, you would have to fill the orbit of Mercury to accelerate that particle. And the only thing I'm sure of, or what I'm going to tell you next, is that's not how it happens. So, to make a long story short, John told us how we built this detector, kilometer cube of ice, with sensors that detect blue light. And so this is what we do. A neutrino comes through the Earth. That's how we make sure it's a neutrino, nothing else comes through the Earth. What does it do? It flies through the detector. But 1 in a million times, it will hit a nucleus in a hydrogen atom, for instance, head on. And what does it do? Make a nuclear reaction. This nuclear reaction may all kinds of particles, but 1/3 of the time it makes a muon, which is usually considered as a useless elementary particle, but in this case it's not, because this muon flies at the speed of light through the detector. And it makes this blue cone, and that cone tells us where the muon comes from and where the neutrino comes from, and that's where we have a telescope. So nuclear reaction, the neutrino disappears, makes a muon, the muon goes at the speed of light through the detector. And of course, nuclear particles make blue light. That's why the particles coming through the water covering this reactor, that's why it's blue. So they tickle the atoms and make blue light. That's what it does in our detector. Why the shock wave, this blue cone? Well, it's the same here. You see this duck. The duck is the neutrino. We cannot see the duck, but we see the waves, the shock waves it makes in the water. And the neutrino makes the shock wave not on water, but on light, in light waves. So we have a telescope. And then it was easy. Here is the realization of the picture. This is a neutrino that comes, muon, that comes from about 11 degrees below the horizon through the ice and makes this fantastic event. This event actually is such high energy that it's very improbable that it was made in the sky. And John showed you two more of these events. I cannot resist showing one. I showed this all over the world to tell people where I live. And so this event is superimposed on the data center, which is one block of the Capitol Square on West Washington Avenue. And so you see it covers about 5 city blocks. It has 300 of these sensors seeing light and tell us in detail what it saw. More than 100,000 photoelectrons, for those who knew what that is, are detected in this event. And we saw this too by accident, that John told Bert and Ernie. And then we worked another few months and we found 28 more. Once they had shown them to us, we could know how to look for them. And then we published. And 2 weeks later, we were declared the breakthrough of the year. And what happens then? Then you don't sleep anymore at night and go over what could have gone wrong. Fortunately, by now, we have detected these neutrinos in at least 4 different ways. So I sleep very well at night. The problem is, where do they come from? Well, I explained to you, they tell you where they come from by the Cherenkov light. They emit the blue light, they emit in the detector. Well, let me tell you the problem. This is 1 year of neutrino data. Every single one of these gray dots is a neutrino. What do you see? Nothing. There is a good reason why you see anything. These are neutrinos produced in the atmosphere. And they dominate the sky. So it's like you're looking at the clouds and the clouds never go away because the next year it's the same. However, I also gave you a hint. The atmosphere cannot really produce these very, very high energy neutrinos. We understand the neutrino emission from the atmosphere. So these very energetic neutrinos, the sky cannot produce. So after 4 years, we saw this. And what do you see? Well, nothing. We can do a more sophisticated statistical analysis of this. And I can guarantee you, you see nothing. After 10 years, finally, we began to see some structure in this map. But that we were not patient enough to do that. So we tried, I'm stuck again. We tried something else. What we tried was very simple conceptually. As soon as we detect a neutrino, the signals go to the surface where we have computers. The computers figure out where the neutrino came from. And then we send that information directly over Iridium to every astronomer in the world who wants to pay attention. It's as simple as that. So a telegram goes out with the precise coordinates of the neutrino within less than a minute of when the light is detected 2.5 kilometers deep in the ice. That was our desperation to try. We looked for help. And on September 22nd, 2017, we started this program a year before. We detected this neutrino, not really special, but it had an energy of 290 TeV, so it was probably cosmic. And so what we did is what we usually do, send these, do I have to do after every slide now? Okay. Send out the coordinates. And a couple of days later, someone noticed that this wasn't in the direction of one of these supermassive black holes that was mentioned by John in the previous talk. In fact, we were hit it within 0.06 degrees, which is much better than the pointing of the detector. And that, as an accidental probability, it could be an accident, like 1 in 1,000. And such accidents happen in science, it's not the discovery. But then, 5 days later, a flux was detected of very high energy gamma rays from this source, which made it already a lot more improbable. But the critical thing was, of course, what do you do at this point? Maybe I shouldn't turn this off anymore. What you do at this point is you publish, of course, but that was not as easy as you think, because we had no clue whether anyone ever looked at these telegrams we sent, except that at some point, more than 20 telescopes were actually pointing in the direction that we had sent out. And one optical telescope looked at the source after 40 seconds. And so this began to look interesting. It wasn't, the neutrino came from this active galaxy, which surprisingly was 4 billion light years away, not close at all, which is a mystery we're still trying to understand. So what do? You publish with the 20-something telescopes, which was a real headache, the first paper. However, the second paper really clinched this business, because what do? We now have a point in the sky to look. So let's look at our data in the last 10 years in that direction. It's an obvious idea. And we look, there it is. And you're probably all looking at the wrong thing now. What I've been talking about is this, the orange line is the number of neutrinos in the last 9.5 years from that direction. You see this little blip at the end, that's what I've been talking about. We found in our data this big thing that labels 2015. That, of course, clinched the detection, because when you look at your data just without adjusting any analysis, it's very unlikely that this is a fluctuation. So the accompanying paper then presented this, this finding. So what do we do next? Because after all, after 10 years, we discovered cosmic neutrinos with one source. We cannot wait another 10 years, so we have to do something better. And that Professor Liu is going to explain to you. Well,
thanks, Francis. You can hear me, right? Okay. Cool. So I'm going to talk about the future of IceCube, but before I go into that, I would like to take a moment to appreciate that we can see each other tonight. So that is because we have a fantastic photon sensor in our body that's called eyes. So when you look at surrounding area, so in our eyes, we have receivers for the blue light, green light, and red lights. So that's how we see color. And we know from the previous talk that the visible light is only a very small segment of the entire electromagnetism. This so what you see here essentially is the energy distribution of photons. On the very left, you have the radio wave, which are the low energy photons of about 10 to the minus 6 electron volts. And in the center right there, visible light. So the light in the light bulb here is about 1 electron volts. And then as you go to higher energy, so UV light will be 10 electron volts, X-ray, they can penetrate through your skin. So this is about 10 to the 4 electron volts. And then you have gamma rays. So these are the highest energy photons that Francis was talking about. So they could go to 10 to the 6 electron volts or 10 to the 9 electron volts. So now actually we have detected the PUV gammas. But the problem is at the highest energies, the universe is not transparent for the gamma rays. So to look at the high energy universe, neutrinos are our hope. So they are actually the ideal messengers because they travel from directly where they were accelerated and travel in straight lines because they don't carry charge. So you see the problem is how to detect them, and we have IceCube detector. So this picture shows you a neutrino interaction in IceCube, and you see this shower. So these are the secondary particles generated from neutrino interaction, and each dot there is one of these guys, the PMT. So this light sensor actually is very similar to our eyes. So they also see color. The difference is they can see wider range and they're more sensitive to our eyes. So they can see a little bit UV especially. So imagine if you're a PMT, the sensor, the world must be more colorful or confusing. So the future, we're optimizing our detector from 10 to the 9 electron volts to 10 to the 19 electron volts. That's 10 orders of magnitude of energy. And the reason we do this is because we're in this fantastic location of really transparent eyes. And this is our one of life opportunity to actually expand our science to much wider range. So you see, that is IceCube, the blue dots. So the string distance, the whole distance is about 250 meters. So at the moment, we're in the stage of upgrading IceCube. So that means we're going to infill 7 strings into this center region of IceCube. And you can see that scale is 25 meters. So it's going to be very dense. So that is because we want to focus on low energy neutrino detection. So it's going to be occupied with a lot of this type of sensors, so we can see more light. And then IceCube Gen 2, so that is the optical IceCube expansion. So we're going to expand this. So the blue region here is IceCube, and we're going to build the optical sensor outside by a factor of 10. And then we also have the radio Gen 2 expansion, which I will be introducing later. So you can see that's a 5 kilometer scale. So that's our final goal, to occupy the entire South Pole. So this Gen 2 is planned construction from 2024 to 2032. And if you're a high school student, you might want to join IceCube Gen 2 to analyze your data. So for the upgrade, we want to do a precision measurement for the neutrino physics. So you see this is a zoom in. So for the IceCube, vertically, so this dome to the next dome is a 17 meter. And for the phase 1, for the upgrade, it's only 3 meters. So that's really challenging. When you deploy these domes, you have to be extremely careful. And the string spacing is really very close. So it's very, it's a technical challenge that we have to come across. Also, what's interesting is so the top guy is this guy. This is our current IceCube eye. What we are going to do is to have this new type of sensors. So on the right here, so this is like an egg shape. So it's an ellipsoid. It's called D-egg. So it's going to be able to see both up and down. This sensor can only see light from bottom, but that one can see both up and down. And this one is like a disco ball. So this is also like a fly's eye. So it sees photons from all different directions. And this is probably where we're going for in the future. Okay, so neutrinos, as we know, some people say is chameleons of space, or some people say they're actually Schrodinger's cat, but neutrino version. So what they actually refer to is something called neutrino oscillation. So neutrino has identity crisis. They're not really, if you see an electron neutrino, it doesn't really mean it's electron neutrino. It's actually a quantum superposition of different mass states. So it's a superposition of all this different flavor. So if you have a mu neutrino in the beginning, as it travels to more distance, so this animation, you can see the distance changes, it actually oscillates. So to the tau neutrino flavor, and also with a probability to the electron neutrino. So the governing equation is shown here. So I'm not going to go into it, but it depends on how far it travels, or is the energy of the neutrino, the mass of the neutrinos, and also some mixing parameters. So this is exactly like Schrödinger's cat, because Schrödinger's cat is a mixture superposition between the leftness and the deadlifts. But this is just 3 types of neutrino mixing. So the oscillation length, as you saw in the equation, actually has some dependencies on the energy of the neutrino. So what you want to measure is neutrinos coming from the other side of the Earth, going through, and then you detect at the South Pole. But you want to be at this distance such that the oscillation is maximum. So we did this calculation, and in fact, oscillation length is compatible to the Earth's diameter only at the lowest energies for IceCube to be done. So the Earth's diameter is about 12,000 kilometers. And you can see this x-axis is the distance. So at 25 GeV, the neon neutrinos would actually reach ideal case for us to do this oscillation measurements. So you see, as it goes further and further, the probability of being neon neutrino is decreasing, but being the so the tau neutrino is increasing. So in the end, it's very likely that you see from IceCube, this event is a tau neutrino instead of a neon neutrino. Okay, so as I mentioned earlier, we now have better ice, so we could see low energy neutrinos in the upgrade much better. So this is a simulation of 21 GeV tau neutrino, and you see this is what we saw before with IceCube, and this is what we see now with upgrades. So you have more light, and you can understand where this event come from much better. So let me just say one more thing of this slide. One advantage we have as is we're not really a fixed target of the length for neutrino travel. Neutrinos can come from Australia, can come from Argentina, then the distance that it travels is different. But that's another advantage for us, actually, to probe different energies of neutrino oscillation. So this is a fundamental physics measurement, and we can actually get quite a lot of very exciting results. So I'm just going to highlight one. So this is to search new physics. So what it does is if you have 3, in the standard model, we have 3 flavors of neutrino, and the sum of the normalization should equals to 1. To make this measurement, we can use tau neutrino, and this is very unique to IceCube because tau neutrino is the production threshold is very high because the mass of tau is higher. And so then if you look at this plot, it demonstrates all these experiments running on Earth to measure neutrino oscillations. So most of the experiments actually are not sensitive to this tau threshold. That's what makes IceCube very unique. So this is the projection of what we will be able to do. It's just a 1 year of data taking with upgrades. So this right line you see, so this is the simulated result. So the plots above, you see, if it's a standard model, then the maximum value should be 1. So you see the gray and blue are from different experiments, and the yellow was from the previous IceCube measurements of 3 years. So what's interesting thing was for the IceCube results, we actually saw this value less than 1. So this could be an indication of something is not working standard model. When the neutrinos oscillate, this is already beyond standard model because neutrino has mass, so that's why they oscillate. But the standard model does not predict that. So this could be something actually very interesting and exciting So this is a simulation if we assume that nature actually has the normalization in this yellow band. Then within 1 year of data taking, we'll be able to actually differentiate whether the standard model is correct. Yeah, so there's a couple of other measurements we can also do, but I'm just not going to go into details. So now we're going to higher energy. So for Gen 2 optical expansion, we're aiming at 10 times larger, and it's called Gen 2. And there is a penguin called Gen 2. It's Gen 2 penguin. So basically, we're going to expand our strings with larger string spacing with about 120 additional cables, 12,000 optical sensors, but this is subjected to optimization. So one goal we have, so this is the beautiful event actually Francis was describing, happened in 2017. So this was this high energy neutrino that we saw from a direction of a supermassive black hole. So you see this beam here is actually is accelerated from nature. So that's all we do. We try to find high energy particles that are accelerated by nature in the laboratory that we can test either energy that cannot be reached by human technologies. So what's remarkable here is with IceCube, you can see this event, the flare was in about 150 days, and the discovery, the significance for this detector was about 3.5 signals. So usually in particle physics, discovery can only be claimed at 5 signals. So with Gen 2, we did a simulation, and if we were detected this event in Gen 2, we can shoot up to more than 10 signals. So that's the power of this high energy upgrade called Gen 2. Another very interesting physics, also very down to my heart, is what are the origins of the highest energy particles? So this highest energy particles, protons, are what explain the process clock. It's been there detected for about a century, but we don't know where they come from because these particles are charged. So when they go through magnetic fields, they bend. However, IceCube actually discovered this diffuse neutrino flux. So before IceCube, there was nothing. So we actually put this on the plot. So these are the cosmic rays, these are neutrinos, and these are gamma rays. So very interestingly, so this energy flux, the energy density of the PeV neutrinos are at roughly the same level with ultra high energy cosmic rays. So usually when nature does that, it means these two messengers actually are linked. So there's a very strong, very interesting question that we want to understand whether these two things actually are from the same origin. Because if they do, then for the first time, we might be able to understand the origins of ultra energy cosmic rays and to study particle physics at this natural labs. So just by the way, this is one of the highest energy events we detected with neutrino energy more than 10 PeV. So we certainly have flux over here, but this is where we are at the moment with IceCube, and the blue dots, so these are the projections with Gen 2. So it's super exciting, and I just hope Gen 2 could be doing as soon as possible. So another a big upgrade we're going to do is for the radio sector. So this is a rather new technology, a new concept. So this is called asterion radiation. So when you have a shower developing in the medium, so usually this, for instance, in the eyes, this shower creates an excess of electrons or photons. So it's rather like a moving charge or a moving battery. So when the charge moves, it will generate in the front as a coherent radiation and in the radio band. So you actually expect to detect very strong radio signals at this cone. So another very interesting thing about radio is they don't really bend in the eyes unless the refractive index changes. So the scatter can be neglected for radio, unlike optical. So optical photons, they will scatter quite a lot in the eyes, and it's very hard to understand where they come from. But for radio, they rather travel in straight line, and they don't really get absorbed as easily as optical photons. So that means if you detect the highest energy, for radio, they can travel much further, travel in a straight line, and it's just very ideal to expand the detector to much larger size, and it makes sense. And another thing is you can build them rather shallower. In this case, our design is only down to 100 meters, while for optical is down to 3,000 meters. So it will be more cost efficient, and for physics, actually makes sense to expand ultra high energy detection with the radio technology. Yeah, so this is a just artistic impression of when an ultra high energy cosmic ray hitting the atmosphere and generate this gigantic shower. So on the surface, this radius could well be about 10 kilometers. So it's a really spectacular shower, but we don't know where they come from. So the idea is we want to detect neutrinos of such high energies. So we want to detect neutrinos of 10 to the 18 electrovolts, or even 10 to the 19 electrovolts. And this red band shows you the sensitivity of IceCube Gen 2 radio. And you see the blue there, this is where IceCube is coming at. So you see 2 orders of magnitude difference. And this gray band shows you where the expectations are from theory. So with IceCube Gen 2, we're well below the theories, and it's promising that we might be able to see the first ultra high energy neutrino, and therefore reveal what are the home, like where these ultra energy particles come from, and how they were accelerated, and to test the fundamental particle physics with these sets. So this is one summary slide I have. It's the future. So we want to have upgrades to cover the low energy region, a GeV region, the optical region to enhance our measurement from TeV to PeV, and then expand our energy range all the way to the highest to discover this ultra high energy neutrinos that has never been seen before. Okay, so yeah, astroparticle physics is about to do fundamental particle physics, but also to understand their sources, propagations, accelerations. Yeah, that's the end of my talk, but just advertisement. So I have this, we have this augmented reality app, so you can download on your mobile phone. And whenever IceCube gets a real-time neutrino alert, you get an alert, and then you can actually see this event on your mobile phone in the hologram. And yeah, so keep in touch with IceCube in this way. Yeah. Thank you very much.
Thank you all very much. And by this one. Oh, yeah. Or go ahead. All right. Thank you all very much for coming. Now, question. Yes, please.
I have a sort of odd question, Francis. When the LHC was being built, people knew that if Higgs boson is going to be discovered, the Nobel Prize will be divided to Peter Higgs and maybe Francois Robert. And most likely this was the same for LIGO and Barry. So what do you think IceCube should discover such that you can get a Nobel Prize? I can rephrase the question. What is the fundamental question that IceCube is trying to answer which deserves a Nobel Prize?
Let me answer this backwards. We had this idea here in Wisconsin to try to use ice instead of water. The idea to build a neutrino detector was proposed in 1960 already, but the idea was to do it in water. And in fact, it was tried, but the experiment failed. And so we had this idea to do it in ice. And, you can imagine what we said when we said, well, you shouldn't do this in water. It's much easier to put photomultipliers 2 kilometers deep in ice at the South Pole. You can imagine how well that went over. And then after a while, people thought this was a great idea, but it anyway wouldn't work. So our only goal was to build this detector. And the most exciting time in this project was when we discovered that we could measure neutrinos in the atmosphere because that meant the technique worked. And it was much more exciting than to discover cosmic neutrinos. So I always had the idea, if we can make this work, we'll discover things. And in fact, we only covered the astrophysics of what we discovered. And, you know, we are so busy. The last thing I'm thinking about is what it takes to win the Nobel Prize. I can guarantee you.
Other question? Andy?
Have you had any correlations with the media using microwaves? They haven't watched that many balloons, but they see more high energy particles.
Can you repeat the question?
Yeah, the question is, there is an experiment. In fact, it wasn't mentioned. It's a very interesting experiment that actually uses the radio technique that Lou explained. But they have their antennas not in the ice or in water or anywhere. They have it hanging from antennas hanging from a balloon that circulates over Antarctica and measured neutrinos that come out of the ice. And so they kind of look above IceCube's head. The problem with these techniques is that they only can detect neutrinos of very, very high energy. And so we don't know whether there are any there. Lou explained, we see cosmic neutrinos now up to an energy of, in my TeV unit, 10,000 TeV. Even the highest energy neutrinos we see, that balloon cannot see. So, and we don't know if there are any neutrinos of that energy. So it's kind of, they're covering a totally different domain. You know, we cover this dark universe I introduced. They are even further on the dark side of the moon than we are. So there's really no overlap. If they would see something, of course, hopefully we would see it too. So there is a word that has not been mentioned, multi-messenger astronomy. So these days, everybody talks to everybody else, no matter what type of telescope, what type of neutrino detector. And of course, you saw an example of how 20 telescopes could find something that we would not have found.
A question from the Zoom audience. If you're building a series of ice cores next to each other in close proximity, then after the neutrino hits the first core and a muon exits the core, will it enter the second core and so on? And is this of any value in research and understanding?
Yeah, I'm not,
Yeah,
I don't know if we understand the scenario. Is it different?
Oh, I understand now.
Okay.
By core, the question means string.
Yeah.
Okay.
Different strings.
Yeah.
Yeah, so I think if we
yeah,
understand,
right.
I think if we
Right,
understand the
yeah.
question,
Yeah,
does
it means
if the first string detects a muon, does it keep going? Certainly the answer is typically yes. The muon has high enough energy to travel through the detector. And as you saw in some of these event views, we see it from one string to the next string to the next string, and use that timing to reconstruct the direction that the muon is going. if we understood the scenario.
Yeah, actually, for most of the data we take, we don't look at the events unless at least 8 strings light up.
Any questions from the audience? Yes, in the back.
Yeah, that's a
Repeat the question.
yes. So I can repeat the question. It was when we were talking about I was talking about IceCube operating 10 years, and I showed this kind of yearly heartbeat, and the question was more information about what causes that heartbeat. So as most of the particles that IceCube detects at many thousands of times a second are actually muons that are produced in Earth's atmosphere, not neutrinos. And so this heartbeat is actually tracking the seasonal variations in the temperature and the density of the air above the South Pole. So as the seasons, as it gets very cold at South Pole, obviously, as it gets colder and a little bit warmer at South Pole, as the density of the upper atmosphere changes, the number of muons that are produced in these cosmic ray interactions in very high up in the atmosphere changes. And so it's this annual seasonal variation that causes this heartbeat that I showed.
Would like to point out that the Zoom transcription is making muons into nuance. Next question here from the Zoom. Is there any plan to research neutrino detection in the ice area of the moon?
I actually, if you spend that long doing something, I was actually at some point on a committee that looked into that question. And not particularly that question, it was to generate ideas of what science you could do on the moon. And I shouldn't quote the numbers, but if you realize what it costs to bring, 1 ton of anything to the moon, it's pretty much clear that it's very difficult to do neutrino physics there. It would be fantastic because the moon doesn't have an atmosphere. And but it's just prohibitively expensive to build a detector there. It was thought about.
Great.
So I don't remember what the experiment's called, but I think someone wants to drill holes in Enceladus. So they want to actually take the ice sample in the moon, it's called Enceladus, and then maybe we can actually put some radio antenna also inside this little moon. But I'm not so sure.
I don't know if we considered that seriously, but
Okay.
it's a long time ago.
That's another question not related to Nobel.
Thank you.
You properly mentioned that according to standard model, neutrinos should be massless, and the fact that it is massive, it is beyond the standard model. But we know that also the W and Z bosons and also the fermions should also be massless. But we add a scalar field like a Higgs field, through the Higgs mechanism, they acquire mass. So is there a way that we can kind of change the standard model Lagrangian and give neutrinos mass? I heard something like seesaw models, but that's for kind of, if you can explain this, and maybe I can just attach my second question to this. What is the really importance of the neutrinos that causes the United States to kind of change gear from focusing on from energy frontier to cosmic frontier and density frontier? I mean, I have a background in LHC, I remember a CMS experiment, and I understand the importance of that and the richness of the physics of the Hadron Collider, for instance. But maybe you can emphasize a little bit the importance of the neutrinos for understanding of the universe.
Well, that was a 2-part question. If you'd like to rephrase, restate the first one,
Please go.
and then we'll restate the second one. So first restate.
Okay, the first question was, the standard model predicts that a neutrino has no mass, and we now know neutrinos have mass. So there must be physics that's not in the standard model that you are looking for at the LHC, and we are looking at with our neutrinos, of course. I mean, we see neutrino interactions that let me now, 1 GeV that are 1,000,000 times higher energy than the neutrinos they produce at Fermilab. So we obviously have the opportunity to detect physics beyond the standard model. In fact, it's kind of disappointing. And, you know, we are working with neutrinos that are so extreme in energy, in the distance they have traveled. And all the standard model predictions are confirmed. When we look at our data, and we can completely understand everything we see with the standard model.
So with this experiment, you can validate the standard model as such a high
Yeah,
energy
of
that
course.
no
The whole,
accelerator
when
can
we
do.
analyze the data, it's all done assuming the standard model. Muons are the same muons that they see at Fermilab. Neutrinos are the same neutrinos as they see in Fermilab, even though they come from 4 billion years away, they behave exactly like standard model neutrinos. Of course, this may change tomorrow, that's the goal. You know, we have a whole group that is looking into this physics, of course, with the hope not to confirm the standard model.
Yeah, so Francis is absolutely right. So at the moment, we don't have any observation that is against the model, but one issue is we don't have enough statistics. So it could be that with accumulating more statistics, we could see the median changes or something like this to make measurement more significant. So that's why also we want Gen 2, because for the highest energies, we only measure like few tens of events per year for the neutrino, for astrophysical neutrino. That's just not enough to claim. Yeah.
You know, a large fraction of this experiment, we are about 350 people now, is doing exactly that physics. They don't care about what we talked about.
That answer your second question, or should we
Oh.
restate your second question?
Yeah, it was the second question. The first one was if we can have, it was more.
Yeah, I mean, how neutrinos get mass, I'm a theorist, I follow this business. We have no clue.
Question from the Zoom audience. Should the IceCube measurement activity be optimized when sun activity is high, producing neutrinos at a high rate, and the probability of detecting is high with IceCube?
I can try to answer that. I think we talked about kind of these different energy ranges that IceCube can operate. We're focused on the highest energy neutrinos from objects in outer space, and the IceCube upgrade that Lou described will focus on lower energy neutrinos that are produced in our atmosphere and use that to study neutrino oscillations. I did talk about how the sun produces many neutrinos, but actually IceCube those are too low energy for us. So we can't actually detect solar neutrinos. There are detectors, much smaller detectors built in, for example, mines or underneath a mountain, the Super Kamiokande in Japan, or the Sudbury Neutrino Observatory in Canada, that are actually focused on studying solar neutrinos and have used that to basically study and confirm how the sun works, essentially. But it's too low energy for IceCube.
Thank you. Any other question?
So you can figure out which direction the neutrino came from And do you have like, I'll just say hunting parties, like go in that direction and see what's out there, where it came from? And then also, I guess I have the two parts. What kind of precision or accuracy do you have, going billions of light years out there from the direction that you detected it in the IceCube?
Could you restate the question?
Yeah, so the first question is the hunting party to look at the direction where neutrino came from. So the answer is yes, there's a huge party around usually when there's a neutrino happens. So we actually send out these alerts to distribute globally. So the time delay between when the neutrino happens and when this global distributed is about less than a minute. So if you're observatory in Russia, you get a telegram essentially, and then you can just point your telescope to where it came from and send another telegram to tell the world what you find. So this is essentially how we found the event in 2017. The second question, was, what is the pointing accuracy we have? So it depends on which type of neutrino. So if it's a muon neutrino, it usually propagates much longer in the detector, so it looks like a track. Then you imagine it's a track, then you can point very well. So it's usually within 0.5 degree, or it could be even better if it's higher energy one. If it's a cascade, so that means if it's a hadronic interaction or there's no track coming out, then that's a little bit difficult. It's almost like you look at fireworks in the sky, and then you try to find out where did the firework come from. If you didn't know, you shoot upwards and you see a firework look like that. It's almost like that, the cascade. So that will be uncertainty in the range of 10 degree. Also depends on how big the cascade is.
Yeah. And I was thinking about taking into account the incident happened and the rotation of the Earth, the orbit around the sun. And if you take any other movement into account.
That's actually easy at the South Pole.
That's true.
An object in the sky just goes in circles.
Question?
My question is about funding. Who funds this activity? If all of the various universities that you work with, they all chip in some money to fund the operating budget, or is it mostly federal money, or some billionaire or some billionaire?
We wish.
And do you have enough? I mean, do you have the funding to meet the timelines that you presented?
You know the answer to the question whether we have enough. But seriously, in fact, it should be mentioned, the project was totally funded and in the US and still is by the National Science Foundation. And they paid for more than 90% of the telescope. And I think if you have understood anything from this talk, I hope that you understood that this was an incredible gamble. We didn't know if this was going to work, and then we had no clue what we were going to see. It's actually a miracle that what we do with the telescope is actually something we had told of before. And so I don't think this would happen anymore. I mean, the National Science Foundation took a real gamble on this 30 years ago and is still funding all of the US activities. That's partly because the National Science Foundation owns research in Antarctica. That's their domain. And the rest of the collaboration, the other people across all the continents, they are funded by by the equivalent foundations.
So I have something I'd like to let the IceCube folks know. In March of 2009, I just started working at the National Science Foundation. The American Recovery Act, ARRA, had just been passed. And we had an all-hands meeting. It was the day after Armageddon. No, Snowmageddon.
Mhm.
And at this all hands meeting, when they were laying out for the 1,200 people working at the NSO, the prime example of how to track the spending and the impacts on jobs of all this new money, the leading example that they used was IceCube. And they said, here's how this organization has tracked the vendors, city by city, county by county, state by state in Wisconsin. And having, I was on leave from this university, and I was really impressed that the folks at IceCube had such a wonderful organization with tracking the impacts on jobs and where that tax money was going and to which communities. That was a singular event for me in my 20 months at NSO.
I should say this. I think it's important to realize that as a response to that this is probably normally a project like this is done by a national laboratory, Fermilabs out of us, Los Alamos, Brookhaven, you name it. This is, as far as I know, this is the biggest project ever done by a single university. And it was only possible because, it has a great and unique infrastructure. Without the Space Science and Engineering Center and the Physical Sciences Laboratory in Stoughton, we could never have done this. We also had the incredible support of the university from the chancellor through the administration. It was it's difficult to describe the collaboration we got from everyone on campus. And that's what made it possible. I mean, very few universities have this type of infrastructure where you could even try this. And but we had the support from everybody. I still get excited when I talk about the subject, no matter how many times I've given this talk, but I don't get as excited as John Wiley. He would talk about this project and he would say, this is like the Egyptian pyramids, like the Chinese wall. And by the way, he almost knew as much about this project, I think, as I did.
Now one here online. Do neutrinos collide with each other? If they do, what is the end result and is it measurable?
They do in a supernova. At the very early stages of some supernova explosions, there are enough neutrinos trapped that how actually the explosion evolves, we saw pictures of an exploding star, depends on neutrinos interacting with themselves.
And what comes of that interaction?
Well, eventually they lose energy and they stream out. They only do this as long as they are trapped inside the debris of the star. But then once the star expands, the energy is released, they just leave.
Great. Thank you.
You said that these international collaborators, the people are funded by their own institution, by their own government institutions. For these upgrades, are you getting any hardware or infrastructure contributions that are international?
Yeah, this is a big change now because NSF paid for more than 90% of IceCube, the hardware and the construction cost, and now this is different. To operations, everybody contributes. And for the next generation detector, a very significant part of the cost is going to be carried by international collaborators. The upgrade Lou talked about is actually Wisconsin mostly provides the drill, and all the infrastructure of the upgrade is constructed in Japan and Germany and paid for. So Gen 2 is going to be a truly international project.
Question?
Yeah, thank you. Thank you for the amazing presentation. I had a question about, so you have the IceCube, and then there's also the radio telescopes in Australia and South Africa, which are also square kilometer arrays. I would like to know, is there a specific reason why you're using kilometers?
In science, I think this is true. I mean, we use kilometers. Even as Americans, although I don't know if I can say that, we use kilometers. I remember when I arrived in Wisconsin in 1971, you could see the distance from Madison to Milwaukee in kilometers on the belt line, with the hope that everybody would convert to metric system. We know what came of that, but scientists use decimal system. Yeah, that's not unusual.
Any other questions? I have a comment that I would like to echo, and that many of us do. Congratulations on your great success. Thank you for a wonderful presentation.